Welcome back to Historical Geology. I am Robert Lopez. We're going to look at the three types of plate tectonic boundaries. The first one is called divergent, and divergent boundaries have tensional stress where there's pulling apart, and that's where we see the mid-oceanic ridges, the seafloor spreading. Tensional stress and divergent boundaries occur in the oceanic setting. We see a lava called basalt. And basalt is a mafic rock rich in magnesium and iron. Think of M and F for magnesium and iron, rich in, and they're going to be lower in silica, no quartz in them. If it occurs in a continental setting, a rift where you're breaking up a continent, for example, and here the East African Rift Valley is a good example. Here we can see basalt and rhyolite. So rhyolite is felsic rock. Felsic rocks tend to be rich in silica. Think of this SI for silica. So high in silica, quartz, potassium feldspar. Remember, orthoclase is potassium feldspar. And the type of rocks we see is rhyolite, which is the volcanic rock. At convergent margins, we see compressional stress. So the force over the area there is compressional stress. And note that there are three subcategories here, where two oceanic tectonic plates are involved. A good example are the Aleutian Islands or Japan, where ocean lithosphere is subducting under another ocean lithosphere. We get volcanic arcs like the Aleutian Island chain or the Japan. And usually we get a rock called andesite, which is intermediate in composition, which is somewhere between felsic and mafic. And usually that rock is called andesite. That's an ocean to ocean, so usually we call that a Japan type margin. For the ocean to continent, where here an ocean plate subducts underneath a continental tectonic plate, usually we call that an Andean type margin because the Andes Mountains are really the classic example. And here we have big stratovolcanoes, primarily erupt andesite lava. And there is an ocean trench, the Peru-Chile trench, so that'd be Andean type. In fact, that's where this word andesite comes from the Andes Mountains, arc or volcanic island chain. And the reason they're called arcs is because on a globe, they make a curved surface, right? Curved structure of volcanoes, and you'll see that in a moment. The third boundary, continent to continent collision or Himalayan type. Here, two continental landmasses crash into each other, so India is crashing against Asia. And really what has to happen is at one point we had an ocean basin, an ocean to continent margin, and the other side of this ocean basin, there must have been a continent, and as the ocean basin closed, the two continents collided. There is some minor volcanism, and it could range from rhyolite to basalt because the crust is getting overthicking. Some of that crustal rock is melting. And then finally, the third type of tectonic boundary is a transform margin, or the transform boundary, and this is like the San Andreas Fault. And here we have a fault valley or a fault where two tectonic plates are sliding past each other. So the type of stress we see here is a shear stress. Like if you had a deck of cards and you can kind of slide them past each other, that would be a shear type of stress. Now, one more type of rock that I didn't mention up here is this ultramafic rock. So this is very rich in magnesium and iron, and this is the rock of the mantle. Usually it's peridotite, although in Earth's early history, in the Archean and earlier, we had some of this peridotite melt completely to produce komatiite lava. So we don't see these anymore because Earth is not hot enough. Is the mid-Atlantic ridge, and these are basalt lava. So when that magma erupts onto the seafloor, it quenches and it forms a structure called pillow basalt lava. And so it's quenched by the seafloor, pillow lava. So the ocean floor is really covered by this pillow basalt. Here's a step-by-step progression of developing an ocean basin. For example, let's say we had Pangaea, a supercontinent here, back in the Paleozoic, and then we begin to start to tear the continent in two by causing magma to upwell underneath the continent. We see volcanic activity, and eventually the continent tears in two, and we get this rift valley. So a good example of this would be like the East African Rift, where you see Kilimanjaro and Mount Kenya, so big volcanoes in that rift valley. So as more time goes on, more magma upwells, the continent starts spreading, so now we start seeing a divergent boundary until we develop a narrow ocean basin. And we develop these fault blocks where crustal blocks slide down relative to one another. And the type of faults we see here are really called normal faults. So we'll talk more about those later, but we see the normal faults here. And we get this narrow seaway, and a good example here would be the Red Sea. So the Red Sea is a good example of a narrow fault-bounded sea. As time progresses, the ocean basin widens until we actually get an ocean basin like the Atlantic Ocean. So this is kind of the progression going from Pangaea to the Rift Valley to a narrow ocean basin to finally getting an ocean basin. So here's a map of the East African Rift where we're seeing Somalia and Ethiopia here rift or break away from mainland Africa. And so this is that Rift Valley, so we'll see volcanoes like Kilimanjaro and Mount Kenya would be in this region here. And then as we go to the Red Sea, so that's an example of a narrow seaway, and also the Gulf of Aden to some extent, a narrow seaway. For the convergent boundaries, remember I said there's ocean-to-ocean convergence, and so that we call that the Japan type. The other one is the Andean type, where we see an ocean plate subducting under a continental plate, and we still have a trench. A good example of the Andes, where we see the Peru-Chile trench. Here in Northern California, Oregon, and Washington states, we have the Cascadia Trench, and we have the volcanoes, the Cascade Volcano, from Mount Shasta or Lassen Peak all the way up into British Columbia, including Mount St. Helens. Then continent collision, that's the Himalayan type where we develop these mountains, and really, like I said earlier, it's a culmination or the end product of an ocean-to-continent convergent margin there. So here is ocean-to-ocean Japan type convergent margin. So here's Japan. So the ocean trenches here. This Pacific plate subducting under the Eurasian plate here, and right at the edge here is Japan. So we have ocean-to-ocean convergence. There's a little bit of back arc rifting or spreading in the Japan Sea, the marginal sea here. But the key thing is we see this volcanic chain. It's called an island arc because they're volcanoes, and usually they have this curved. That's what they're called, arcs. Now for an Andean type margin, ocean to continent, well, they do have the Andes here, right? So usually when you see a line like this with the teeth on it, that means it's a reverse fault or a convergent zone. And so here, this oceanic plate is going down, and the South American plate is being thrust over the top of the ocean plate here. So sometimes we call it a thrust fault. And what happens here is, note, we're going to have a chain of volcanoes, like the Andes volcanoes. And these also occur in a curve. See the curvature there, and then it curves this way there. So that's what's called in fact, these are called a magmatic arc. So the Andean type volcanoes are magmatic arcs, whereas the island arcs, or Japan type, are island arcs. At some point, the ocean basin is going to close. So note that in the Himalayas, we still see this oceanic crust up there in the convergent margin of that ocean basin that existed between India and Asia, and it's since been closed, and these two continents have since collided to make this large mountain range, the Himalayas. So this is an example of continent-to-continent collision. And usually when we find fragments or sections of oceanic lithosphere, oceanic tectonic plates, in a continental setting, we call those Ophiolites. How do we recognize these ancient convergent boundaries? Well, we look for igneous rocks, right? We look for those volcanic rocks. What are the andesites, those stratovolcanoes? So we look for the types of deformation where we want to see that compressional stress, those forces that lead to convergent margins. And a term we use in geology here is a French word called mélange, and mélange means mixture. Here it's chaotic mixture of folded, faulted, metamorphosed sediments and marine rocks. Usually this mélange refers to the subduction zone complex, the accretionary wedge that occurs before the volcanic chain, the volcanic arc. So it's where all the ocean floor sediment and even fragments of ocean lithosphere, the actual pillow basalts and maybe even fragments of the mantle, are being scraped off and mixed up in that subduction zone. And then I mentioned ophiolite. So this would be the ophiolite in here in the Himalayas. And so these ophiolites, they have a very systematic or stratigraphy, but it's really how they formed at the mid-oceanic ridge. So what happens is, at the bottom we have the mantle, upper mantle peridotite. Remember I mentioned peridotite, that ultramafic rock forms a mantle. Then we see these layers of gabbro, because imagine as a mantle partially melts, it makes magma chambers, and the magma chambers, as minerals solidify, they settle to the bottom of the magma chamber. That's why we see these layers of minerals in the layered gabbros. Then we have this massive gabbro where some of that magma begins to cool, solidify, and harden. So we see a plutonic rock with big crystals, so that's the gabbro. But remember, these were once magma chambers, and they're shooting magma up to form the pillow lavas. So we get these vertical structures called sheeted dikes. So those are intrusions from the magma chambers up to the volcanoes, and then that magma erupts as lava to make the pillow lavas. So pillow lavas at the top, sheeted dikes, then the magma chambers, the gabbros and layered gabbros, then the mantle underneath that. And then as the seafloor starts moving away from the mid-oceanic ridge, well, the marine sediment begins to collect on it. So that's always at the top. The deep sea marine sediments are going to be on top of the pillow lavas. For the transform plate boundaries, remember I mentioned that they're sliding past one another, side by side. And the type of stress we see here is that shear stress. And then the San Andreas Fault is a good example. And really these transform faults are offsetting mid-oceanic ridges here. So these are the divergent margins, and then there's an offset transform fault there, then another divergent, then another transform right there, another divergent over here. So in California, we have a mid-oceanic ridge off of Oregon and Washington State called the Juan de Fuca Ridge. And then there's a transform fault here that offsets that ridge. And then off of California, we call this ridge the Gorda Ridge. So the Gorda Ridge, and little tectonic plate here we call the Gorda Plate. It's just the southern part of the Juan de Fuca Plate. And then everything over here to the west is the Pacific Plate. But then from the Gorda Ridge, mid-oceanic ridge, there's an offset. It's called the Mendocino Fault up here, but then the Mendocino Fault turns into the San Andreas. So the San Andreas would be a big transform fault, and then there's a mid-oceanic ridge down here. And this is part of the East Pacific Rise, that huge mid-oceanic ridge that's going to go all the way across the east side of the Pacific Ocean, right? So that's a giant mid-oceanic ridge. But you can see that the San Andreas Fault is a transform fault that's offsetting a mid-oceanic ridge, from the Gorda Ridge to the East Pacific Rise here. Another criteria we use for plate tectonics are these hotspots. And the key thing about hotspots is that they're mantle plumes that rise through the mantle. But the key thing is that they follow a stationary path. They're not moving, they're just going straight up. They're not flowing left or right, they're just moving straight up. What's happening is the tectonic plates are moving over these. It's like holding a match under a piece of paper and moving that piece of paper across that match. You would leave a burn mark, and that burn mark would move in the direction that you're moving the paper, right? So in this case, earlier I mentioned that the only active volcano in the Hawaiian archipelago is the Big Island. Then as we go to Maui, Molokai, Oahu, and Kauai, these are older, more eroded. In fact, they're starting to become, eventually they're going to become geos, right? They're going to fall below sea level and get that flat top, those table mounts, right? So the Pacific Plate's moving over this hotspot. And you can see that the Hawaiian archipelago is really part of a huge Hawaiian seamount chain. Most of these are underwater. Midway Island is above water. But then the other chain is called the Emperor Seamount Chain. Most of these are underwater. All these seamounts and former islands, geos, were once here, and the whole plate has moved and carried them away from this hotspot. Now here's a good example. In this picture we're seeing, so another thing I want to mention here, I talked about the word orogenesis, which is the genesis or birth of a mountain. Remember, oro means mountain in Greek. We usually the word use orogeny, and orogeny refers to that mountain building event. And then there's this other term we use called a Wilson cycle. And the Wilson cycle is named after J. Tuzo Wilson. He's one of the pioneers or fathers of plate tectonic. He's one who was really involved in developing the plate tectonic theory. But he was saying, well, you get seafloor spreading, and we get subduction zones. At some point, the ocean basins are going to open up, and continents are going to crash into each other. And then they're going to break up again. And then they're going to spread. And they're going to crash again. So basically, he's saying that these cycles of forming supercontinents, breaking up supercontinents, forming them over and over again. And in fact, in this class, we're going to learn about several supercontinents that have occurred in the geologic past. So really what Tuzo was saying here is that you open ocean basins and you close ocean basins. You're forming supercontinents, you're rifting supercontinents.